to find probabilities involving p hat, our sample proportion, we need to remind ourselves what we know about the distribution of p hat. We know the mean of p hat is equal to the true proportion. The standard deviation of p hat is directly related to that same proportion and the sample size. And we know that the distribution of p hat is approximately normal when n times p hat is greater than 5, that is, our observed frequency is greater than 5, and n times 1 minus p hat is greater than 5. So remember, all that means is we have to have 5 that are and 5 that are not in our category. And again, if the sample has not yet been taken, we're going to check to see if it's reasonable to expect that we will end up with at least 5 that are and 5 that are not in our category. And we do that by using p as an estimate for the sample proportion. And so we check n times p hat and n times 1 minus p hat. Make sure both of those are greater than 5. Okay, so as long as that's true, p hat will be approximately normally distributed. And then we can use all the tools that we normally use, so to speak, for the normal distribution. Once you've established that the distribution of p hat can be approximated by a normal distribution, define the probability that p has between two numbers. Okay, and again, those numbers may include a positive or negative infinity in there. We're going to use our normal CDF, putting in our limits that we have on p hat and the appropriate mean and standard deviation for the variable p hat. And so the mean of p hat, remember, is p. The standard deviation of p hat is the square root of the quantity p times 1 minus p divided by n. And as always, if something's normally distributed, we could, if we wished, right, convert that to a z-score. And so to do that, we have to take the variable, in this case p hat, minus the mean of that variable, p, divided by the standard deviation of that variable, okay, which in this case is that square root of p times 1 minus p over n. And as long as your variable, in this case p hat, is normal, then when you standardize it, you get z. In our first example, we're rolling a fair 12-sided die 19 times. Okay, we want the probability that more than 50% of these 19 rolls turn out to be multiples of 6. We don't know what's going to happen with the 19 rolls. We're saying, what are the chances that more than half of the 19 rolls turn out to be multiples of 6? So we want the probability that p hat is greater than 0.5. In order to find this, we have to know the distribution of p hat. We know to check, since the sample hasn't been taken, is n times p hat going to be greater than 5? And it turns out in this case, again, sample size 19, probability of getting a multiple of 6 is 2/12. So that only gives us a little bit over 3, which means we don't expect to get 5 or more multiples of 6 in our sample. So the distribution of p hat is unknown. It's definitely not approximately normal, which means we can't find this probability. Okay, you can't always force a distribution on a variable. Okay. In the second example, we were rolling a fair 6-sided die 200 times, and we want the probability that less than 40 of the rolls turn out to be 1s. So we want the probability that p hat, our sample proportion, is less than 40 over 200, or less than 0.2. And again, 0.2 would be perfectly fine to use here because that's the exact value of 40 over 200, not an approximation. To do this, we need to know the distribution of p hat. So we have to check to see, again, the sample hasn't been taken, so we need to know if it's reasonable to expect at least 5 1s and 5 that are not 1s. And since n is 200 and the probability of rolling a 1 is 1/6, we expect about 33 of the 200 rolls to be 1s and about 167, give or take some, not to be 1s. So we clearly reasonably expect to have way more than 5 rolls that turn out to be 1s and 5 that are not 1s. So p hat can be approximated with the normal distribution. Since p hat is approximately normally distributed, we're going to draw our normal graph. Okay, I want you to notice far right hand corner, we've labeled the graph p hat. So the sample proportions are the numerical values on our axis. The mean of these sample proportions, the mean of the p hats, is right there in the middle of the graph. And again, the mean of p hat is the true probability, and the probability of rolling a 1 is 1/6. Okay, so 1/6 is about 0.166 repeating. 0.2 is a little larger. So we want the probability that p hat is less than 40 out of 200 or less than 0.2. So that's why we shaded everything to the left of the 0.2. So we need to use our normal CDF function, lower limit -infinity, upper limit 0.2, and we need to insert the mean and standard deviation for p hat using our formulas. And we know that p, the actual probability of getting what we want each time we roll the die, is 1/6. So we're going to replace this p, right, with 1/6, and n was 200. So everywhere we had a p, I've replaced it with 1/6. N is 200. Go ahead and enter it in exactly like this. Don't round the terms in the middle. Okay, this way the normal CDF is operating on the exact values and you minimize your total amount of error. And your final answer should be as accurate as possible. And so in this case, there's a 0.8970 probability that less than 40 out of the 200 rolls will be ones. For this next example, we're going back to the Peyton Manning passing data while he was here at UT. And we want to know, if we randomly pick 10 of his pass attempts, what's the probability that less than 7 of those 10 were completions? So we want to know the probability that p hat is less than 7/10 or 0.7. To do this, we need to know the distribution of p hat, which means since the sample hasn't been taken, we don't know how many completions are actually in the 10, because we don't have any choosing the 10 yet. We need to check to see if we expect to have at least 5 completions and 5 incompletions. So we do the n times p, and 10 is our sample size. The probability that a random pass is complete is 863 out of 1381. So we do expect to have 6.2 roughly completions, which only leaves us 3.8 incompletions. So we don't expect to have at least 5 completions and 5 incompletions. Now, we also knew that from the beginning because our sample size was only 10. Right? If there's only 10 in your sample, there's no way you're going to have more than 5 that are and 5 that are not in your category. So the distribution of p hat cannot be approximated by a normal distribution. Right? The distribution of p hat, therefore, is unknown, right? Which means the probability cannot be found using the tools we have in this class. This time we want to know what the chances are that if we randomly pick 100 of his completions at UT, that somewhere between 6 and 12 of those passes turn out to be touchdowns. So we want to know the probability that p hat is between 6 out of 100 and 12 out of 100, or 0.06 and 0.12. We need to check the distribution of p hat, which means we have to know if it's reasonable to expect to have at least 5 touchdowns out of the 100 attempts, and at least 5 that are not touchdowns. So we do our n times p, and again, p is the probability that a completion is a touchdown. So there are 863 completions to choose from. 89 of those are touchdowns. N is 100. Multiply that by that probability. We get about 10.3. And I can either do the multiplication or I can subtract 10.3 from 100 and get 89.7. So yeah, we expect to have about 10 touchdowns and about 90 that are not touchdowns. So even if we're off by 3 or 4, we're still going to have more than 5 of each. So p hat can be approximated by a normal distribution. And so we can use that information to find this probability. Since p hat is approximately normal, I'm going to start where we always start, with a graph. And label it p hat, draw a normal curve, The mean of p hat is equal to the true probability, 89 out of 863, okay, which is slightly bigger than 0.10. So 0.12 will be a little bit to the right of that, 0.06 will be a little bit to the left, and we want the area in between. Because p hat can be approximated by a normal curve, we're going to find this probability using the normal CDF. Our lower limit 0.06, our upper limit 0.12, and then we need the appropriate mean and standard deviation, okay, which are both based on the true proportion, 89 out of 863, and then also the sample size for the standard deviation of p hat. So replace the p's, all three of them, with 89 divided by 863. N is our sample size. We are randomly picking 100 passes, so we're going to place N with 100. And again, I'm going to insert all these values in the calculator and not do any rounding of the in-between figures, so that we get the most accurate probability that we can here. If you were to round that big square root down to 2 or 3 decimal places, okay, that's going to affect this answer, and you may not get it right when you do your online homework. By now you should recognize that the problems I'm using here were the ones we started in the distribution of p hat video. Okay, so this time we're talking about the amount of time it takes the hill route to make one loop around campus. And we know that that time is normally distributed with a mean of 24.4 minutes and a standard deviation of 3.9 minutes. And the question we're trying to answer is, if we randomly pick 140 round trips, what's the probability less than 10% of them take more than 30 minutes? So, in other words, what is the probability that p hat is less than 0.10, right? 10% is a proportion of 0.1. To do this, we need to know the distribution of p hat. Since we haven't collected our 140 round trip times, we have to see if it's reasonable to expect that at least 5 of them will take more than 30 minutes and 5 won't. So we have to do our n times p check, which means we need to know p, the true probability of a single round trip taking more than 30 minutes. So this is where the fact that the round trip times are normally distributed comes in. The probability that a round trip, right, lasts more than 30 minutes is going to be found using the normal CDF. We want 30 minutes or longer, so 30 to infinity are my lower and upper limits. Our mean was 24.4 and our standard deviation was 3.9. Okay, so this is our true probability. We need to check n times this to see if that's bigger than 5. So n times p, 140 times 0.0755 gives us 10.57, and n times 1 minus p, 129 and change. Okay, so since there's about a 7.5% chance that a round trip randomly would be more than 30 minutes, okay, we expect out of 140 trips to have about 10 or 11 that will take more than 30 minutes, and about 129, 130 that won't. Okay, so both of those are definitely larger than 5. So p hat is approximately normal. Because p hat is approximately normal, I can use all my normal distribution tools. You can start with the graph of p hat. We want the probability that p hat is less than 0.1. The mean of p hat is equal to the true probability. So the probability of getting what we want each time we do the experiment. And the probability that we have a round trip that takes more than 30 minutes each time we check is approximately 0.0755. And we got that using our normal CDF function once already. So to find the probability that p hat is less than 0.10, we need to use our normal CDF from negative infinity to 0.10 with the appropriate mean and standard deviation for p hat. And so those are given by p and the square root of p times 1 minus p over n respectively. We know that p is the actual probability that a single round trip takes more than 30 minutes, which is approximately 0.0755. So I'm going to replace all three p's with 0.0755 and n with 140. And when we do that, we should get an answer of approximately 0.8637. And again, this is the probability that less than 10% of our 140 random round trips takes more than 30 minutes. I want to take one more look at that last example. Okay, just to remind you that we always have the option when something's normally distributed to convert to z-scores instead of adjusting the mean and standard deviation in the normal CDF function. So because p hat is approximately normal, we can use our conversion p hat minus the mean of p hat, which is p, divided by the standard deviation of p hat, which is that big giant square root. And if p hat is approximately normal, this conversion will turn p hat into a standard normal distribution. We wanted the probability that p hat was less than 0.10, so we're going to place 0.10 for p hat. And p and n are still 0.0755 and 140. And so a sample proportion of 0.10 equates to a z-score of 1.097, approximately, with a little bit of rounding. Okay. Now, we wanted p hat to be 0.10 or smaller. And if we replace the 0.10 here with something smaller like 0.09, 0.08, 0.07, right, the smaller that number is, right, in the first spot, the smaller that z-score will be. So the probability of getting a p hat value that is less than 0.10 is going to be the probability of getting a z-score that is less than 0.1097. So we would use our normal CDF from negative infinity to 1.097 with the mean of 0 and a standard deviation of 1. And we get roughly the same answer minus any rounding that was caused by calculating that z-score first. Again, we don't expect you to do this every time. We just need you to make sure you're very aware that anytime something is normally distributed and we want to find probability or even percentiles for that matter, we have to make sure we account for whatever the appropriate mean and standard deviation are. And one way to do that is by converting to z-scores. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!